Okay, so right off the bat, we're going to kind of talk about some scheduling changes we're going to make. Um, as far as our class meetings for face-to-face and hybrid, that is not going to change. That will remain the same. So on that initial schedule that I gave you, if it was a hybrid day, it is staying hybrid. If it was a face-to-face meeting, it is staying face-to-face. Um, what I am going to change is that at our next face-to-face meeting, you guys were scheduled to have a test. So that is the week after your spring break. I'm going to change that up a little bit. You guys will have a quiz over that material, but we will not test on it. And so what that means is that it's not a day where you would come in and take your test and then leave after your exam. So we need to make up the labs and a couple other things that we missed in losing out on our last face-to-face meeting, and that's how we're going to recover some of that time. So make sure that you bring all of your materials for digestion, nutrition, and then our conversation that we're going to have over the urinary system. That needs to come with you to our next class. We will start out the face-to-face meeting going through the activities and other things that we need to do, and then the last hour you guys will have to then move into the quiz part um, and get that taken care of. At that point, once you are done with your quiz, you will be able to go. So we're going to start off with what we need to cover, start the quiz around 5:30 that evening, and then you will have the remainder of class to finish that. So when we're looking at the urinary system, and technically this part of our conversation is really going over the entire excretory system. When we talk about the excretory system, that is referring to all the ways that your body removes any waste product from your system. And there's quite a few ways that we do that. Um, they kind of fall into other systems, and so we're able to talk about them and cover some of the different ways just when we go through like our integumentary system. One of the ways that you get rid of waste product is through sweating. We talked about that when we went through our skin information. With your solid waste, that pulls into the digestive chapter. So the large intestine pulls out the excess water, turns that chyme mixture into a solid material, and then you will void it out of your system. That's another way that we get rid of waste. When you guys exhale, you're getting rid of carbon dioxide, which is a waste product that our cells have produced. And so that's another way. So when we talk about the excretory system, we are referring to all of the different ways that your body gets rid of waste. I did narrow this down to just cover the urinary system because, as I mentioned in other conversations, we've kind of already picked up those other topics. So this is going to be focused, but please understand that when you are talking about the excretory system, you are covering any and all ways that your body is going to be able to eliminate any waste that it produces. And we will always produce waste because nothing works at 100% efficiency. So the urinary system is going to be our topic for this evening. One of the biggest things, if you look at that first slide, it talks about the urinary system being a major part of homeostasis. There is a lot of regulation that goes on in what is eliminated from your body. And based on what's going on in your system, where different levels are at, your body can allow more liquid to leave, it can hold on to liquid, it can determine based on your salt levels, things of that nature, how to make changes just to ensure that you guys are not eliminating anything from your body that you could potentially reuse, that you're not eliminating things that you are already low on, or that you are getting rid of more of a particular substance that you have way too much of. So, this is a very fine process of your nervous system working through monitoring the conditions of your body and then determining how it's going to relay that information to your kidneys, to the other structures, so that the right amounts of things are either held back or let go. So, when we look at that urinary system, one of the biggest things that it's going to do is it's going to help regulate the pH level of the body. So pH for human beings should remain about 7.4. So we are slightly on the basic side when you look at that pH scale. Um, Part of that regulation, and we talked about this earlier in the year, but pH level is one of the things that we have in our body that actually has a very small um, degree of range that you can have before things start becoming problematic. So, with your body temperature, you can fluctuate 6, 7, 8 degrees from that standard of 98.6. Um, with your pH level, you only get a very small range. We're talking about 5 hundredths from your normal pH. And once you start ranging too far away from that, um, things will start to shut down and not work the way that they're supposed to. So 7.4 is the pH level that you should be at. When you get to 7.45, then you're going to start seeing things change in the body or not working the way that they're supposed to. And the further you get away from that, the faster those things are going to start shutting down or not work the way they're supposed to. On the other side of it, when you get to 7.35, now you're going to start seeing problems the other way. So, really, when we look at pH, we have a very small degree of change that the body can tolerate before there's going to start being adverse effects that are associated with that. So, the kidneys really hone in on making sure that that pH level is where it's supposed to be. And then also making sure that your body fluids are where they need to be. So the kidneys can hold back, like I said, liquid. If you are dehydrated, you don't have enough fluid in your body, the kidneys can actually hold some of that back so that you maintain it. Because remember, the body always works on the idea, the concept that you don't know when your next meal is going to come, when your next glass of water is going to come. And a lot of the body functions that we have today still work off of that caveman era where they were having to hunt their food. They didn't necessarily have access to clean running water all the time. And so, or they wouldn't have, but um, just that unknown. And so over time, the body really developed ways to make sure that when you did get access to those materials, we had a way to conserve it so that if you ever lost that access or didn't have availability to food, water, and things like that, you could preserve yourself for as long as possible. So even to this day, we see our kidneys regulating that very, very specifically, just because even though we have access to running water, you can go to at pretty much any store and grab a bottle of water at any time. Our body still works off of that idea of really not knowing when or if that next serving of liquid is going to come. Your urinary system, it also talks about removing metabolic wastes. And metabolic waste is just referring to any of those waste products that are made through the process of our body doing basic work. So when your cells do work and they give off that waste product because they don't work at 100% efficiency, that is going to fall into that category of being metabolic waste. Also, we come in contact with things all day, every day. A lot of us will go home and clean our houses and not think twice about getting chemicals and different things on our hands as we're going through that cleaning process. That actually can get absorbed through your skin and then get into your body. And that is a foreign substance that is not supposed to be there. So your body has to regulate that and make sure that if those foreign substances get into your system, we have a way to get them back out. And sometimes we do self induce those foreign particles or materials. So if you are ingesting illegal drugs and things like that, again, it's not something that is supposed to be in our body. And so our body will work to remove that. So when we look at the urinary system, we have four main structures. We have the kidneys, you have the ureters, you also have a bladder, as well as the urethra. And those are the four main structures that are really going to work together to make sure that once your body has created that liquid waste, we now have a way to get it out. If you look at the second slide, it gives you a little bit of a visual representation of those four structures. And when you initially look at the kidneys, one of the first things that you might notice right off the bat is that, excuse me, your left kidney is going to be slightly higher than the right kidney. And while the other organs have been removed from this picture so that you can't see them, the liver would be over the right kidney. And because of the shape of the liver, so it's kind of triangular, the bottom part of it cuts diagonally through the core of the body. So, because of that slant angled shape of your liver, that kidney is positioned just a little bit lower to make sure that the liver has all of the room that it needs. You'll also notice that there are two structures sitting right on top of the kidneys. Those are the adrenal glands. We'll be talking about those a little bit later. So, from the kidneys, that is where the actual urine formation is going to take place. Once that is created, we have to have a way to get that down to the bladder so we can eliminate it from our body, and that is going to be the job of the ureters. So, there is a tube that extends from each of the kidneys down to the bladder, and it actually is going to attach. It's a little bit difficult to see on this picture, but it's going to be coming into or exiting, however you want to look at it, from the middle part of the kidney. So it's not coming out of the bottom of the kidney, it actually comes from the side of the kidney, and it will then make its way down to the bladder. So the bladder is going to hold all of that collected liquid until we're ready to eliminate it from our system. And as that fluid is created, it's not created in a kind of, you turn on your faucet and you get running water all at once. That's not how this is going to move from the kidneys down to the bladder. Each drop of liquid, kind of think of a leaky faucet, one drop at a time. That is how most of the urine is going to be delivered to the bladder, just simply one drop at a time down into the bladder. And so it does take a period of time for you to build up enough where the bladder is actually going to then signal that you need to eliminate that from your body. And then the last one is the urethra. This is going to be a tube that is going to extend out of the bottom of the bladder and ultimately take the urine out of the body to the outside world. So the first thing that I want you guys to take a look at on the third slide, the internal anatomy of a kidney. So the picture on the left, we've actually cross-sectioned a kidney. You are looking at the core of it. And then you also have a pull-out picture, which shows you a nephron. Now, the kidney itself is basically an assembly line. There is a process of pulling the material out of the blood and then funneling it to get it to where it needs to be. And so we kind of work from the outside in. If you look at that picture, you'll see the renal capsule. So there is a covering that is over the entire kidney itself. And part of that renal capsule is going to be in place because remember, we are pulling out material that is wasteful and potentially could do harm to the body and the other tissues. So we want to make sure that we have an extra barrier there just to make sure that nothing can leak out and move into the surrounding tissue and structures. You also can't see it on this particular image, but the kidney is going to be completely covered in fat as well. When we do our dissections of cats and things like that and we open them up, a lot of people will immediately tell me they don't have any kidneys because they are just completely covered in fat, and all of you see is that yellow fatty material, and you have to cut through that to actually get to the kidney. That's to offer extra protection to the kidney because in the human body, most of our kidney hangs below the ribs, and because it doesn't have that bone protection, it needs that extra layer of fat to help protect those kidneys so that they don't become damaged. The next two structures that you'll see there, the renal cortex and the renal medulla. So the cortex is just underneath the capsule, and then in from that, we have the medulla. And if you look, you can see how they bracket it out. You can see that those are two different layers within that kidney structure. Now, within that cortex layer, that is where you are going to find the nephrons. And the nephrons are the smallest functioning unit of the kidney. So this is where urine production is actually going to begin in that little nephron. And each of your kidneys is going to have in the neighborhood of 1,000,000 nephrons. So they are just jam-packed in there. But if you think about taking 1,000,000 of anything and packing it into a structure that is basically the size of your fist, they are incredibly small. And so earlier when I was talking about urine production happening drop by drop, that's why it happens in that fashion, is because those little nephrons are forming that urine, because of their incredibly small size, the amount of urine they produce at any one time is very small. So we have the nephrons in that cortex layer, and then you'll notice in the next layer, the medulla, you have these fan-shaped structures that are known as, or referred to as, the renal pyramids. The average kidney is going to have somewhere between 8 and 10 renal pyramids, and they just kind of fan around the entire kidney itself. And this is really where the assembly line begins. So the nephrons are going to remove material from the blood, take out what it wants, and then move that filtered material out and forward so that we eventually can eliminate it from the body altogether. So from the nephron, the next phase is that filtered material is going to move into that renal pyramid. And if you look at any one of those renal pyramids, you'll notice that it eventually tapers at the bottom and turns into what is called a minor calyx. So it sounds really fancy. It's a funnel. So we're taking that liquid. You can see how the backside of those renal pyramids are pretty wide and how they would have contact with a lot of different nephrons. So those nephrons are producing that filtered material. It's going to drip its way into the renal pyramids. And now the renal pyramids are just going to funnel all of that material into a minor calyx. The minor calyx, if you continue to kind of look at the neighboring renal pyramids, you'll notice that the minor calyx from one pyramid eventually merges with the neighboring minor calyx, and they get a little bit bigger. And if you continue to look, the one next to that, they will merge together. When you get multiple minor calyces merging together, that is going to then transition into what is known as a major calyx. So we go from the nephron, it's going to pass that filtered material into the renal pyramid. Renal pyramid is going to move it towards the minor calyx. The minor calyces are going to merge together into a major and just keep building all of that liquid and that fluid together. So eventually it's going to come into the renal sinus, or the renal pelvis. And that is going to have all of those major calyces merging together into, it looks kind of cluttered on the picture, but it's a opening that you have where all of that funneled material is going to come together, and we're eventually going to make it's eventually going to make its way into the ureter. So anything at that point that has made it that far in the process is going to be eliminated from the body. It is on its way out. One structure that's on there that we didn't talk about yet is the renal papillae. That is simply where the pyramid, the renal pyramid, and the minor calyx fuse together. So where those two pieces actually meet and come together, that is going to be the renal papillae. Quick explanation of the structures that we have within the kidney, just understanding that you have multiple layers, that renal capsule plays a very important part in making sure that everything within the kidney stays housed within the kidney and cannot leak out. And then just that funneling process of getting all those tiny little drops of filtered material moving forward and in one direction so that they can collect together and then eventually make their way down to the bladder itself. If you move to the next slide, it has a picture of the kidneys along with some of the major blood vessels that you have. And if this picture were in color, the one on the left would be in blue, the blood vessel, and the blood vessel on the right would be in red. So the blood vessel that you have on the left, that is the inferior vena cava. So that has collected blood. It is now tracking it back up to the heart. So if you want to put an up arrow on that inferior vena cava, blood flow is making its way back towards the heart. The one on the right, that is the abdominal aorta, that blood vessel that we have, the largest blood vessel that we have in the body. Blood in there would be tracking down. You'll notice that both of them have branches off of them, renal veins, renal arteries, and those are running in and out of the kidneys. you have a large amount of your blood supply that is running to your kidneys at any given time. Filtering our blood and making sure that it is constantly cleaned out is a huge task, and it's very important because we need to make sure that if there is something in our body, it's not allowed to circulate through our body several times before we get it out. So these two blood vessels are dedicated to making sure that that blood is consistently and in large volume run through those kidneys to keep it clean and reduce how much exposure our tissues and other body parts have to any toxic material that we might come in contact with. With the adrenal glands that you have sitting on top of the kidneys, those glands are going to be, and we're going to talk about these more when we get into our endocrine chapter, but these two glands sit right on top of the kidneys because when you guys get in stressful situations, that those two are going to be responsible for that fight or flight response. So adrenaline is going to come from those adrenal glands, and by being attached to the kidneys, and you can see the blood vessels working their way to and from the adrenal glands. If you get put into a stressful situation, your body can immediately dump that adrenaline into your bloodstream. And if you look at the size of those two blood vessels, you know immediately that that adrenaline is going to have access to a huge amount of blood, get dispersed out to your body very quickly, so that all of the changes that need to take place and need to happen for you to either fight or to flee are going to take place in a very small amount of time. So I wanted you guys to see that design and kind of really think about why that is so important. Number one, to make sure that we're filtering a large amount of blood all the time, keeping it as clean as we possibly can to limit exposure. And then why the placement of those adrenal glands is so important, especially in times of stress when we need to get that adrenaline out to our body parts. The next slide that you guys have talks about what the kidneys do for the body, and we kind of hit on this. Actually, we're going to skip over that one and go to the nephron slide. So, as I mentioned earlier, the nephrons are your most basic structure that you have within the kidney. So, we always have a basic functional unit. When we talk about living things, that would be the cell. When we talk about chemistry, that would be the atom. When we talk about muscles, it was the sarcomere. When we get into kidneys, now we're looking at the nephron. So the nephron has a very specific design to it so that it can do its job the way that it needs to. And I pulled out just one single picture of what a nephron looks like so that you can really get an idea of how that works. So within your nephron, you are going to have a capsule. And that capsule is going to have a series of blood vessels that are going to run into it. The blood vessels have a fan shape to them, and so they kind of coil and create that fan. So the blood will come in, it will run through that fan shaped series of blood vessels, and then the blood will run back out. What happens in between is extremely important. If you look at the capsule surrounding the nephron, you'll notice that at the back of the capsule, there's an exit. So that material that is filtered out or pulled out of that fan shaped structure is going to then make its way down into that tube. So the blood comes through, moves through that fan shaped structure, and pretty much all material is going to get filtered out at this point. Red blood cells will be an exception, they will never get filtered out. And then a lot of the proteins that we have in our blood are also going to get filtered out at that, or a lot of the proteins will not get filtered out because they're too large and they can't pass through. But a lot of the other material that you guys have in your blood at that point is going to get pulled out. And that material that is pulled out of your blood is called filtrate. So the rest of the blood that's still in the fan shaped structure, and that is called the glomerulus. So technically, that fan shape, that is the glomerulus, and it will run back out and then go back into your body. That filtrate material that gets funneled down, that is going to now go through a filtering process. Because even though it was initially pulled out, some of that material in that filtrate can be used in the body again. And our body tries to be as efficient as it possibly can be. So if there's any material in there that can be used again, still has some sort of benefit to the body, we're going to make sure that we get it back into our bloodstream. So if you look at the next slide, it shows a series of tubes, and I would strongly suggest you pulling your textbook out and pulling this up and looking at it in color. Because if you look at it just in black and white, it's just a mess of all of these tubes running back and forth, and it's kind of hard to distinguish. In your textbook, you have a colored picture of this, and it's in red and blue, and then kind of a tannish beige color for the convoluted tubes. So what we have going on here, if you look right at the middle, you can see that glomerulus, so that fan-shaped structure of blood vessels. So we know that is where the blood is actually going to get filtered. The tube coming out of the back of that area, so that is going to carry all of the filtered material, but we need to get some of it back into our body. So we're going to run that filtered material through those tan or beige colored tubes. And if you look at that, you'll notice that after we get a little ways from the glomerulus, all of a sudden that tube narrows, becomes smaller. Nothing in the human body happens by chance. So if all of a sudden we have this wider set tube transition and become more narrow, there is a reason for that. And what actually happens is if you have a certain amount of liquid running through a tube and all of a sudden you reduce the size of the tube, what did you just do to the amount of pressure that is being applied to that liquid? Think of a sponge. Pick up a sponge, has water in it. When you squeeze that, all the water gets forced out. So the change in size with that tube is going to increase the amount of pressure that is on that filtrate. And you'll notice that right where that happens, you have a whole network of blood vessels that run right over those tubes, those narrow tubes. This is where the filtering process actually happens. Those materials that still have benefit to the body are going to get squeezed out of those collecting tubes, and they're going to get forced back into the blood vessels. That's why it's incredibly important that those blood vessels and those collecting tubes are so close to each other and that you have that network of blood vessels right over the top of it so that that material that has benefit can easily make its way back into our bloodstream. So you have that kind of dip within the tubes. That is going to be where the movement happens. Beneficial stuff moves back into the blood vessels. Anything that truly is waste product is going to remain in that collecting tube and will eventually be eliminated from the body. The other design feature that I want you guys to pay attention to is if you look at that collecting tube as it makes its way through the blood vessels, you'll notice that it eventually turns and starts to swing back up. So you have the ascending loop, you have the descending loop, and then you have the ascending loop. Again, nothing in the body happens by chance. So if we have this specific design, there is a very real reason. Think about if this were a road and you are driving on it in your car. You come up on that hairpin turn, what are you doing with your car? More than likely, you're going to brake and slow down. So what this actually does, by having that loop there, we're slowing down how fast that filtrate is moving through the collecting tube to make sure that we give our body all the time that it needs to move that material across so the good stuff goes back into the bloodstream and that it has enough time to get that done. So that's a very important design feature that we have. As we swing and come back up through that ascending loop, you'll notice that the blood vessels kind of lessen. We don't have that thick network of blood vessels because at that point, anything that hasn't been filtered out of that filtrate material is leaving the body. So it's missed its chance to get pulled back in at that point. You'll also notice that the tube becomes wider. So it's going to start moving a little bit faster, and then it eventually is going to lead to a collecting tube that will link up with the ureter. and move it on to the bladder. So a lot of things going on within this nephron. It's a tiny little structure, but it does so much for our body and making sure that our blood stays clean. So the next slide that I want you guys to take a look at, you have a slide that refers to how urine is formed. And there are three main parts to urine formation. The first one is glomerular filtration. The second one is tubular reabsorption. And then the third one is tubular secretion. We have talked about all of those. So when I just took you through that picture of the nephron, we actually hit on all those steps. I just didn't use those terms quite yet because I wanted to explain the process as a whole. So glomerular filtration, that is that initial piece where when it goes through that fan-shaped blood vessel, that most material, remember not all, but most material is going to get pushed out of the blood. It goes into the collecting tubes and starts navigating through all the twists and turns of that collecting duct until it eventually gets to that loop portion. And that's where tubular reabsorption is going to happen. Reabsorption is just referring to any of those products that can be reused by the body are going to get pulled back into the bloodstream or the blood vessels so that we can recirculate it and get it to where it can be used within our system. So if it has some sort of benefit, if it can be reused, it's going to get moved back into your blood vessels through that reabsorption process. At that point, anything that has not been reabsorbed is going to be deemed as waste product that needs to be eliminated from the system, and it is going to make its way into the bladder, and that is that secretion process. So then removing or eliminating any of that product that has no benefit to the body. So the next slide that you guys have is a filter rate. So it talks about how much water is filtered out of the blood. So 125 mils per minute. And if we were face to face, I would have you guys actually measure this out and take a look at it. Every minute to have 125 mils, it's not going to take very long before that actually builds up into quite a bit. So if you think about over a 24-hour period of time, how much that would actually equate to, and I'm actually going to have you work through this. So 24 hours, 125 mils every minute, what would that actually transition to? And I gave you some conversions there. Keeping in mind that of that initial material that is pulled out, 98% of it is going to get reabsorbed. So during that reabsorption process, 98% of it is going to get pulled back into the body. I gave you a conversion rate of the quarts and how many mils that equals, and then quarts and how many gallons that equates to. I want you guys, for our next class when we come back, to have that figured out. So 125 mils per minute. How much would that be within a 24-hour period of time? And if 98% of that is reabsorbed, how much are we actually going to eliminate from the body? Now, I'm going to type this up as an assignment, but this is your go-to sheet for that information that you will need to complete that. So when you go to Blackboard, you will see the questions for this typed up and exactly what I expect you to be able to provide me when we have our next face-to-face meeting. So when you look at what urine is actually made of, it talks about most of it is going to be water, which probably does not surprise most people, that an overwhelming majority of that is going to be just the water content that you put into your system. So we talk about having 64 ounces of water every day. And with that, stretching that out over 24 hours is pretty important. It's not drinking huge amounts of water all at once just to say that you got 64 ounces in, but making sure that from the time you get up to the time you go to bed, you have spread that 64 ounces out is going to be very, very important. You are going to have some materials such as urea, uric acid within the urine that eliminates from your body. Now, urea is going to be the material that actually colors your urine. So that is going to have that yellow content. And depending on how much water you're actually voiding will determine how concentrated that urea is. So if you have a lot of excess water that you are able to eliminate, it will dilute that urea, and so it will not appear as bright yellow. If you don't have a lot of excess water, that urea is going to remain concentrated, and you will see a much more vivid, vibrant yellow color that's being eliminated from your system. This is also why your sweat will stain light colored clothing yellow, because one of the products of sweat is urea. And we talked about this in our integumentary chapter. But for those of you that weren't with us first semester, that yellow discoloration is actually the urea that is being eliminated from your system through the sweat that you produce. You also could potentially have things like amino acids. So those are your building blocks for proteins and things like that. And then electrolytes. So electrolytes are going to be those positively and negatively charged um, ions that have come together within the body. If you pay attention to sports drinks, that's one of the things that they will kind of advertise is that they have electrolytes. Sounds really fancy, but it's just telling that you have a positively and a negatively charged um, element that have come together. And then the last piece on there, again, kind of talked about this earlier, that the amount of urine that you are eliminating is going to be directly tied to the amount of fluid you're taking in. So if you are staying well hydrated, your body will eliminate or be able to give up more of that fluid. If you are not well hydrated, then it's going to conserve and hold back what liquid you do have, just to make sure that you have enough throughout the day to do all the things that you need to do. In the United States, it is predicted that 75% of all Americans are classified as dehydrated. As much access as most of us have to water, readily have to water, we don't get anywhere close to the 64 ounces. Again, majority wise, we don't. And so on any given day, 75% of Americans would fall into the dehydrated range. The next slide that you have talks about the ureters. Touched on these a little bit earlier, but they are the tubes that are going to take urine from the kidneys down to the bladder. It just gives you a little bit of background information on them. Talking about them being 25 centimeters long. Conversion is 2.5 centimeters for every 1 inch. So if you work more on that side of things, just so you can mentally do that conversion. And they are going to run, you'll notice it says parallel to the vertebral column, so just directionally making sure that that material gets moved down to where it needs to be, which is in the bladder. The last piece that I put on there, it does have 3 layers, and not that I would expect you to memorize the 3 layers, but this again is a trend that we've seen in the body, and so I wanted to point it out. A lot of our structures, our blood vessels, our lymph vessels, our heart, our stomach, the uterus, all of those structures have 3 layers. Inner layer, outer layer, and then sandwiched in between is going to be a muscular layer. And so this was just another area where we have that same structure, that same setup. And so I wanted to point it out and make you aware of that. The next one that we have is the bladder. So the bladder is a structure that is kind of interesting because it has the ability to transition in size based on how much material it is actually holding. So when the bladder is empty, it will actually constrict down and be very, very small. And it is made up of a material called transitional epithelium. Now we're going all the way back to the beginning of first semester. Transitional epithelium is when you have alternating cuboidal and columnar cells. And the columnar cells are the tall, skinny ones. The cuboidals are about the same height as they are wide. And what happens is when you start to fill up the bladder, those tall columnar cells will actually start to stretch. And so instead of being tall and narrow, they start to spread out and allow for the bladder to be able to stretch to take on that fluid as it continues to build within the bladder itself. So the bladder is not always the same size throughout the day. It will constrict when it's not full, and then as it needs to expand, it has that ability to stretch and do that. So the average bladder is going to be able to hold about 13 ounces. So if you think of a can of soda, you're looking at just one more ounce than that can of soda. That's an average. Some people will be less, some people will be more than that. And those are adult averages. Obviously, a little kid is not going to be um, in that neighborhood either. The last piece that I put on there, just kind of an interesting fact, um, but if you have somebody that wears heels all the time and so they're kind of on a tilt, it actually can change the position of the bladder and cause the bladder to tilt forward, which it's not supposed to do, meaning that when you would go to the restroom, you would not completely void out the bladder because of that additional tilt. And so the potential for having more urinary tract infections and things like that happens in women that wear high heels. The next slide that you have shows the male and the female urinary systems side by side. The reason that I wanted you to take a look at this is specifically with the urethra. So the urethra in the female is about 4 to 5 centimeters, and note that I said centimeters. In the male, the urethra is going to be 7 to 8 inches. So much different lengths when we talk about the urethra in the female and the male. And it's a structural difference, obviously, because we have different structures in this region. But it also explains why, for um, potty training, a lot of times you'll hear that it's easier to potty train little girls than it is for guys. And the reason for that is you're relying on muscle control to constrict and hold that urethra shut until you are ready to void that urine. And because of the shorter amount of muscle that you have involved around the urethra and holding that closed, compared to the male anatomy, it could potentially impact that. So that is typically why you see little girls maybe potty trained sooner and a little bit quicker than little boys. Doesn't always work that way, but that is the reason why physiologically or anatomically why. The last slide just gives you some information on the urethra as well. Kind of talked through that as well, just looking at those two pictures and kind of comparing those. So we are not meeting face to face this week because that was how it was initially scheduled. Next week is your spring break. And then the following week, we will meet